Here we're going to have a look at metallic bonding, which is the third kind of bonding after ionic and covalent. And we're going to have a look at the structure of it, but also how that structure contributes to the properties of the metal. This isn't actually a type of bonding, so it's really important to remember that actually all metals are a mixture, and you'll see why in a minute. And this video will go on to have a look at the triple content in terms of how alloys work. So let's have a quick look. Now, the properties of metals tend to be things like able to conduct electricity all the time, relatively high melting points. However, there are obvious exceptions like mercury. They tend to be in the hundreds as opposed to the thousands of degrees. So they aren't really very high. Ionic tend to be a bit higher. They tend to be ductile, they tend to be malleable, so they can be bent and turned into wires, and they always tend to be shiny. We're going to have a look at some of those properties. So let's have a look at the idea behind bonding. So if we were looking at covalent bonding, now, and then we had lithium, if each of these are lithium atoms, there's one outer electron on each. So this lithium atom here has one electron, this lithium atom here has one electron on the outside. Now, in theory, they could overlap and they could share those two electrons. The problem is, then they still have 6 spaces around the outside. So we can't share electrons like you would in covalent bonding. Now, you could potentially transfer them. So we had that electron there, and the blue electron there, that goes over to this one, and you have a blue electron. However, you've got a little bit of a problem here, because you would have to do that in the case of lithium 6 more times. So you'd have to take an electron from here, from here, from here, from here, from here, and let's say from there. And that would cause this atom here to have full outer shells and all the others to have empty. The problem is the nucleus of an atom is not strong enough to hold on to 8 electrons, and as a result they will just get kicked off. So they are more stable on the other atoms. So you can't do that. So metals must stay together in a different way. And the way that happens is if we take, let's say, a few different colours. So we've got blue there. These would tend to be dots and crosses, but just for the sake of this, it's easier to draw them as different colours. Now, if the blue one moves from there to there, so it's moved from this atom to this one, what that will do is that will kick this one off, because no longer is the atom strong enough to hold on to that outer electron. So it kicks that one off. And then that one's going to kick off the green one. So the green one's going to go over here, and you get the idea. And then the yellow one moves over here, so it's no longer up there. And what's going to happen is the electrons are just going to bounce from nucleus to nucleus, right? Which means they haven't actually got a home. They haven't got a location, so we call them delocalized. So these are now delocalized electrons. Now, this theory you don't need to know, but it does help understand the difference between ionic, covalent, metallic bonding. But what it means is that all those outer electrons, we'll put them in blue, are now just floating and moving from atom to atom. So they haven't got an actual home. So we call them delocalized, right? So they are now delocalized electrons, and we'd say that we'd describe them as a sea of delocalized electrons. Now, what happens is, because those negative electrons have left the atoms, what they leave behind are positive cations, and they form a lattice structure. So we would then describe this as a lattice of cations. So you would have a regular lattice of cations or positive ions surrounded by a sea of delocalized electrons. So this is your definition for metallic bonding: a regular lattice of cations surrounded by a sea of delocalized electrons. Now, what this means is, firstly, the electrons are now able to move between the ions, which means that they can conduct electricity, because a charged particle needs to be able to move. So that's the first thing. It can conduct electricity because the electrons can move. it is also malleable and ductile. And the reason is because these are not actually chemically bonded, they're held together with the electrostatic forces of the electrons. However, they're not chemically bonded, so they're a mixture, which means that these are actually able to move. So they can actually be stretched out, or they can just be pushed in one of these directions, which would mean that all of these would move, but these and these would not. So this is why they're able to bend and change shape, because of this regular arrangement. It's why you bite gold in the Olympics, because pure gold would bend when you bite it. You'd be able to bend the gold medal. So that's why they bite it, to prove that it's real gold. It would leave teeth marks in it if it were real gold, and because the metal is quite malleable. Now, this is what you need to know for combined, just the fact that it can conduct electricity because of the electrons, that it's malleable, that it has a relatively high melting point because of the strong electrostatic forces that hold it together. However, if you're going on to triple, it's worth knowing about alloying, because if I alloy and I mix together different metals, then I'll still have the same arrangement. I'll still have the lattice of positive cations, like that. I'll still have my C of D localized electrons. But what you'll notice is there's a clear difference now, in that actually they're not a regular arrangement anymore. The actual nice straight lines that you've got in a pure metal, now I've got a different metal ion, because different metals are going to be different shape. Because I've got a different metal ion, actually now no longer can they be forced in one direction. And so they end up having a much more random arrangement, which actually makes it a lot stronger, which is why things like brass and copper are so much better throughout history for building statues and weapons and musical instruments than pure metals like copper. So brass and bronze and steel, for example, which would be alloys, are much better than their raw metals like iron and copper.